Hi, my name is Dan Daly from Intel, and I'm here to introduce Mario Baldi from Pensando, who is going to talk to us about an efficient memory system for high performance pipelines in P4. Thank you.
Thank you very much, Dan. So before starting, I want to just say that this system was designed by Mike Gallas, who is our chief ASIC architect at Pensando. So let me set the context for this presentation, which is the platform that Pensando has developed for implementing distributed services, network services, security services, storage services, across a number of devices, which we call distributed services cards, that are installed in hosts and servers. So the idea is to execute those services at the network edge. These distributed services cards, or DSCs, are fully programmable. They are based on a custom ASIC, and that ASIC contains several programmable processors, and in particular, it contains a programmable processor pipeline, several programmable processor pipelines that are programmable with P4. Now, why did we choose to have those pipelines? And consequently, why did we choose to use P4 to program those pipelines? Well, the basic question, the basic answer is because of performance. As I said, we have other programmable modules on the card, but when we want performance, we want to use those pipelines. And what is specific of a pipeline? A pipeline executes, a pipeline is composed of several stages, and each stage executes a limited task with a small number of instructions, which are, for example, an action in P4, and it uses a simple data structures, which are tables in P4. Okay, so this is generic about pipelines. When we use pipelines for packet processing, we can leverage features that are typical of packet processing to improve even more performance. And the features I'm referring to are the fact that packets require similar processing. Different packets require similar processing. So at the end of the story, we execute a limited set of operation. We need a limited set of operation. And data access, for a lack of better term, is well defined. We want to access tables. We want to access a certain amount of information for every packet. So how can we get high performance out of a pipeline? Well, first of all, since we are dealing with a limited set of operations that every stage has to execute, every processor in the pipeline has to execute, we can optimize those processors for the execution of those specific operations. Since we need to perform table lookups, we can specialize hardware to perform lookups, have specialized modules to perform table lookups. And then, since we are executing small programs in each stage, we could have a fast memory local to the stage for instructions. And if the tables we use are small, we could use a fast local memory also for storing those tables. So all of these will enable us to achieve high performance. And we can see that memory plays a key role in order to achieve the expected performance. In general, the performance of the pipeline, but this will be reflected in the performance of our P4 programs. And as far as our case at Pensando, the performance of the overall solution, because as I said, our service card, distributed service card, includes also some general purpose processors, some specialized processor, and besides the pipelines. And all of these processing elements exchange information through memory. So memory really plays a key role. Now, when we write a P4 program, we might not deal directly with that memory, but still, if the memory system works properly, this is what will enable our programs to run fast, to have the desired performance, and will enable us to write programs that do not have to undergo too many constraints to satisfy too stringent constraints. So what are our options in designing memory for a pipeline? So the first idea is to use a local memory, as I was mentioning before. So every stage has a dedicated amount of memory, and we can use it for data, so for the tables and for instructions, and its memory could possibly be writable. So like, for example, to implement registers in P4, or, as Andy Fingerhut has presented in his talk, in the context of the PNA, portable NIC architecture, we are proposing the availability of tables that can be written back. Now, having a local memory has the advantage, it's a very simple architecture. The access latency is low and always constant. And the solution is scalable, because as we add more pipelines or more stages to our architecture, we also add more memory. So we do not have contention, increased contention, and we do not have overall limit of memory overall. But the memory for each stage is going to be of a limited size. If we need to store larger tables, we will need to split them across different stages. But this means that we're going to waste the processing capability of the stages that we could avoid using if we just had a larger memory in a stage. The usage of memory might be inefficient, because if a stage is not using all of the memory it has, other stages cannot take advantage of it. And because the memory is not shared, the data cannot be shared across stages or, for example, across other devices. On the other side of the spectrum is a memory, a common memory that's shared across all stages. And, again, we can use it for data instructions, can be writable. It can also be off chip. So it can be fairly large. And this is the main advantage, one big advantage. Another advantage is that we are going to be able to use it flexibly, because at this point, if a stage uses little memory, whatever memory is not used by that stage can be used by others. And because it's shared, data can be shared easily across pipelines, across stages, and across different devices. On the other hand, the access latency will be higher, and the memory can become a bottleneck, because at this point you have several stages of several pipelines and possibly other devices accessing the memory at the same time. So it could affect performance. So in between these two options is to have a central memory with a local cache, and the cache will access and will mask the access latency and limit the contention to the centralized memory. So this is possibly a best of breed solution between the previous two, putting together the benefits of both of them. Now, when we use cache, traditionally in general purpose computing, we can take advantage of cache because the programs we have execute have spatial locality and temporal locality. So they tend to access data that is stored in nearby locations. So when we cache from the main memory a bunch of locations, we are going to use them for the current operation, but also for the next operations, we find the data already in cache. And temporal locality, because the program will access that information over and over again in a limited amount of time. Now, especially temporal locality is true also when we go to packet processing, and I'll elaborate a little bit more about this later. But in particular, when we deal with packet processing on a pipeline, we also have another type of locality, which is functional locality. What I mean by functional locality is that a given function is going to access a limited number of instructions and a limited amount of data. So if that function is executed in a certain stage, there is a very high probability that those instructions and that limited amount of data will be in the cache of that stage if we are using a system with central memory and cache. And this stems from the properties that we have said before about packet processing, where we need short programs at each stage, and small tables are commonly used. If we have larger tables, what happens? Well, what happens is that, and we have a system with cache, what happens is that, first of all, packets that belong to the same flow will access the same entries of those tables. Those tables will not fit completely in cache, but packets of the same flows access the same entry, and packets of the same flows are usually processed close in time. So here, temporal locality will help us. So again, in packet processing on a pipeline, functional locality and temporal locality will help with our cache. And of course, if instead we have a large number of flows that are concurrently active, then we might experience some misses. So the idea is I'm going to show you some experiments that will allow us to get a sense of how much this last point is a problem versus all of the advantages that we have mentioned so far. Let me just first take a look at how the memory hierarchy in our chip works. So we have a number of pipelines, and each pipeline has a number of stages that are depicted here at the bottom of this picture. In each stage, we have a level 1 cache, and that cache is used for instructions and for data. So for tables, we have a TE, a table engine that performs table lookups. And the idea is it's going to perform the table lookup in cache. If the information is found in cache, if the table entry is found in cache, the table entry, so the action data and the address of the first instruction of the action are going to be passed to an MPU, a match processing unit. And each stage has 4 MPUs. Now the MPU will independently fetch the instructions, again, from cache, possibly, from the L1 cache, possibly, and then start executing its program. Now, if tables or instructions are not in cache, they're going to be looked up in a level 2 cache that then is going to be backed up by a last level cache, which is shared by the other processing devices on the card. And the last level cache will access the memory. The memory is an off-chip memory that can be even larger. We support up to 64 gigabyte of memory. So this is very flexible. Of course, the question is, what happens when information is not in cache? Now, based on whether information is in cache or not, we are going to have a different access time. So the access latency is going to be variable. And how do we deal with it? Well, when we have high latency, there are 2 options. One is to wait, so stall the pipeline basically. And this is definitely not good because it's going to affect throughput and performance of the pipeline. The other one is to process another packet, start processing another packet for which information is readily available. And that's exactly what we have implemented in our ASIC, in the sense that the table engine is able to issue up to 28 reads concurrently. So whenever the table engine wants to fetch data from the memory, it doesn't have to do it in a serial way, but can generate multiple requests. As soon as one of these requests is completed, the corresponding data is passed to an MPU. So the MPU can immediately start processing the data. So if we have misses, what happens is that those misses are not necessarily going to affect the performance, because while we are waiting for the data to be fetched from level 2 cache or eventually from the main memory, the pipeline is not stalled. The various MPUs are going to be working on data that was instead found in cache. So unless we have really a large number of misses occurring concurrently, the system performance is not going to be affected. Of course, by processing packets based on how quickly the lookups happen, might cause packets to be processed out of order, but every stage has a mechanism that preserves the packet ordering, so that graduates packets to the next stage in the order they were received by the stage. So let me now look into some experimental results to show how frequently we experience misses in this cache, and how frequently instead we find our data in cache. So the kind of experiments I did are based on code for a cloud data center. It's production code. It's the code that Pensando has developed for its distributed services platform. And specifically in these experiments, I've used 2 different P4 programs. And then I used various configurations, so various numbers of features active and various scale of those features. For example, I don't know, like one virtual NIC versus multiple virtual NICs being implemented, and different traffic scenarios, which at the end of the story, in order to highlight problems with cache, translates into having scenarios with different numbers of concurrent active flows. And I've used the profiling functionality of our ASIC that is keeping track of whether reads into level 1 cache produce a hit or a miss, to trace the number of hits and misses on data reads, and hits and misses on instruction reads. So remember, data reads are per stage because they are performed by the table engine, while instruction hits and misses are per MPU because MPUs go and fetch instructions by themselves. And what we can see in this first example, where we have 1,000 active flows, so a relatively low number of active flows, is that the assumptions that we made actually are valid. So let me tell you what we see in this plot. On the x-axis, we have the various stages, and on the y-axis, on the left, we have the number of reads or writes performed by the table engine, in this case, because this is the data cache in thousands. So, you know, up to about 1,800,000 reads. And on the right-hand side scale, we have the hit rate. And as you can see, the hit rate is virtually 100% always. And this happens because, again, the number of flows is not extremely high, so table entries are always found in cache. We see here, we have the blue bars are reads, the gray bars are writes, and they are all happening in cache. We have one stage that is writing back in a table. Now, if we look at a scenario where we have a larger number of active flows, that's where we start seeing a few misses. Still, most of the stages don't have misses because the tables that are being accessed anyway are not large enough they're small enough to be contained in the stages, in the cache in each stage. Where we have misses is because we are dealing with table that depends on the specific flow and that don't fit completely in the cache of the stage. Now, interestingly, we can see that where we have the largest number of misses is with stages that do not perform a very large number of reads, which means that not every packet is experiencing these misses. So this is already a reason why these misses are not going to impact performance. But moreover, as we were saying before, the fact that there is a miss doesn't mean that the processor is going to, that the stage is going to be idle waiting for the read to complete. There are going to be other reads performed at the same time, and if those happen in the cache, then they are going to be used to feed the processor, and consequently the throughput in terms of packets per second being processed is not decreasing. And just to give you another example, this is with a different pipeline. And again, we see a similar situation where most of the stages read always from cache, and some of the stages experience some level of cache misses. In this case, no dot is being plotted because the number of reads and writes was so low that it was not statistically relevant. But we can see again the cache is actually working very well in making sure that information needed to process packets is available in cache, so with low latency, with performance that is completely comparable to the one of a local memory. Very interestingly, or in all of these cases, the instruction hit rate is 100%. So why is that? Well, because the instruction cache is large enough basically to accommodate all of the instructions. This makes sense. We have seen that the common actions in our programs compile to 30 to 50 instructions. And given that our level 1 cache contains up to 2,000 instructions, then we can potentially store in cache 40 to 60 actions per stage, which is more than a general P4 program will need. And so instruction misses are extremely rare. And to confirm that, we aggregated the results across 17 scenarios over those two programs. So there we collected the hit rate experienced by every single MPU. So altogether, we have over 1,200 data points here. And what we see basically is that 98% of the MPUs experience a hit rate higher than 95%. So some MPUs experience a hit rate that's lower. As you can see, there are some that experience, the one that experiences the lowest hit rate is 40%, but it's like really a very few cases, like probably 4 or 5 MPUs out of 1,200 MPUs, let's say 5 cases out of 1,200 cases. So to conclude, we want to use P4 over pipelines for performance and for flexibility. And we have seen that memory plays a key role in the performance and flexibility of the target architecture. And what we have seen with these experiments is that a large central memory with a caching system can successfully provide both performance and flexibility, at least in the scenario that we have looked at, which is in a device that is sitting at the network edge. Thank you.
Great, thank you. This is really interesting. This really looks like something that's super flexible. And one thing that has always been an issue with P4 on switches is just the ability to expand the amount of memory that is accessible. And this looks like a really great solution. My questions were around, so I see it, that the caching and how it's sort of working out in the test that you have. How did that translate to packets per second and bandwidth in that situation?
Yeah, that's a very, very good question. So as I was saying, because when we have a miss, we are not necessarily stalling the pipeline. We're not necessarily waiting while the data is being retrieved, because there is a certain level of parallelism within the stage. It does not or let me say, it should not, in most cases, have an impact. Moreover, in the cases we have seen, misses happen on tables that are not looked up for every single packet. In fact, they happen with a small number in in the stages where they happened, the number of reads was small. However, I think this is a very good question, because I think more work is required as far as experimental work to really go and measure that and
Right.
see that in fact that's what happened, that those packets were not actually held back more than the others.
Right. But it feels like your architecture could hide that, or go and
Yeah.
when it does have a miss, it just goes to the next packet and starts to go through.
Yes.
So it
Yes.
feels
Yes.
like you have that capability there. That's really interesting. And
Yes.
then when you're running that P4 program, are there certain P4 constructs that work better, or are there certain table types that are more easily cached and things like that?
Yeah. This is a good point. In fact, I did not touch on this in the presentation, but our architecture includes also, first of all, it includes also a certain amount of local memory. That's in addition to the cache that the programmer can choose to use to store certain tables. If I know that certain tables are small and are going to be accessed very frequently, then I can put them in that memory. Secondly, we also have TCAMs. So for certain types of lookups, you definitely want to use TCAMs. For lookups that are not indexed or exact. For lookups that are not indexed or exact, if one wants to use the general memory through the cache system, then of course it depends on how that is being implemented, by the how the lookup is being implemented, because of course memory access are still memory access based on addresses. I would say that in general, if the information you're needed, you need to access that memory, the various hash tables that you might want to have are in cache, you're going to get the same benefits. But of course, this is another aspect that would need to be more specifically investigated to make sure. But in general, I would say that our compiler tends to place longest prefix matching, for example, or range matches in TCAM.
Right. Okay. And it feels like your pipeline has so much capability and so much flexibility because of these MPUs that are running. Do you feel like that there are certain things in P4 that need to be added or extended to be able to fully capture or to be able to implement the program that you're interested in?
Yes, absolutely. So first of all, we have this capability of writing back into memory, and we have. I mean, as you know, we are working in the PNA architecture workgroup to include the capability of writing back to tables. And this is very important to us because it's a feature we have and we want to be able to use. Another aspect is the fact that we can, for example, we allow our programmer to specify that certain tables should not be cached for whatever reason, maybe because the programmer knows that those tables are accessed by the control plane in a way that is, not convenient to use cache. So that's also possible. For this, we use table properties. So, P4 already supports this kind of extension. But yes, definitely we do use the P4 to specify aspects that are related to our memory and that are specific to, related to memory and that are specific to our architecture, including also being able to specify that a certain memory should go in SRAM, as I was saying before, in the local SRAM.
see. Cool. Great. Well, thank you so much. I really appreciate you coming in and showing this architecture. This looks really, really interesting. Thank you.
Thank you, Dan. Thanks for moderating.